Hello students, welcome back. Let's have a review on Calculus 2 materials. A real function is said to be analytic around t0 if it can be written as a power series centered at t0 like this, in an open interval centered at t0, which we call the interval of convergence. It turns out that there is a non-negative extended real number, capital R, which we call the radius of convergence, such that this power series converges absolutely when the distance between t and t0 is less than capital R, and diverges when the distance is greater than R. Remember? All these are coming from either ratio test or root test. And the ratio test is a little bit easier to apply, so let's talk about ratio test first. So from here, you can take the ratio test, that is n plus first term over nth term, take the ratio, take the absolute value, and take the limit. If the limit of the ratio is less than 1, then we have absolute convergence. Greater than 1, we have divergence. That's the ratio test. And from here, how can you calculate this radius of convergence? Here's the idea. This limit L is less than 1 than absolute convergence, but then again, t minus t0 to the n plus first power over nth power. This will divide itself out, and we have only t minus t0 to the 1 power left. And times the limit of this ratio. And then flip over this limit to the other side, and consequently we get this limit of the reciprocal. So if t minus t0 in absolute value is less than this limit of this ratio, then we have to have absolute convergence. So this limit is going to be my radius of convergence. So the conclusion, the distance is less than capital R, this radius of convergence, then we have absolute convergence. Greater than R, then we have divergence. Now equal to R, in that case, the ratio test is inconclusive. Therefore, we'll have to consider those endpoints separately using other testings, like what do you call the limit comparison test, integral test, and things like those. Oh yes, alternating series, and so on and so forth. I hope everybody remembers. But there's a good news. This is differential equation, so you don't have to worry about the endpoints. We always consider open intervals only because we have to take the derivatives. So, good news. You don't have to worry about the endpoints. Another way to get the same thing is through the root test. Take the root test, nth root of the nth term, and if the limit of the root is less than 1, then we have absolute convergence. Greater than 1, we have divergence. Now, how do you get the ratio, how do you get capital R, the radius of convergence here? Here, nth power and nth roots cancel each other out for t part here. So absolute value of t minus t0 pops out. And then we have this limit left, which we're going to divide away. Then you're going to get this condition here. When t minus t0 in absolute value is less than this reciprocal, then we have to have absolute convergence. So we can set this one as capital R, and that capital R will become the radius of convergence, and we're going to get this. The distance is less than capital R, then we have absolute convergence. Greater than R, we have divergence. Now, the radius of convergence gives us the interval of convergence. T minus t0 is less than R in absolute value means this. T is greater than t0 minus R, but less than t0 plus R, or equivalently, t belongs to this interval, this open interval. So this open interval is called the interval of convergence, and when t is selected within the interval of convergence, then the series converges absolutely. If it is selected in the exterior, so not just outside, but outside the endpoint as well. So if I select from the exterior, or equivalently speaking, the distance is greater than r, not just greater than or equal to, but strictly greater than capital R, then we have to have the divergence. That's what the interval of convergence does. And within the interval of convergence, we can take the derivative term by term, and we can take the antiderivative term by term as well within the interval of convergence. These two proofs are actually pretty hard, and I don't know whether you can do it in real analysis 1 or you'll have to go through it in real analysis 2. I hope I can do it in real 1, but I haven't taught real analysis 1 for quite some time, so I don't remember. Here are some examples of well-known power series: exponential function, cosine function, sine function, and geometric series, and finally log function. I hope everybody remembers. Maybe the last one is a little bit new to you, because this is not the kind of form that we used to do in calculus. In calculus, we used to do it like this. Log of 1 plus t, and then we used to get t to the nth power instead. Like this. We started from the geometric series formula. And we switch the sign. Let's put some more space in between. And we switch the sign. Come on. So change this into plus. So I'll have to change this to negative t. So 1 minus t plus t squared minus t cubed, and so on. We can do it like this. And then we take the antiderivative. Take the antiderivative of this. So what is this? Log of 1 plus t is equal to antiderivative of 1 over 1 plus t. Oops. Is equal to, now the antiderivative of this. So antiderivative of 1 is t. Antiderivative of t is t squared over 2. Antiderivative of t squared is t cubed over 3. And that's t to the 4th power over 4, and so on. And that's the form we used to use in calculus 2. Here, we took a parallel shifting and replaced t by t minus 1, and you're going to get this expression here. The calculus of power series, okay, we can take the derivative and antiderivative freely, term by term, within the interval of convergence. Outside the interval of convergence, we can't do that. Final topic, index shifting. It's not the final topic, excuse me. Next to the last topic, index shifting, we already discussed it, so let's skip and let's go over to the final example here. Differentiability versus analyticity. What's the difference? Let's go back to Taylor's series expression here. Yes, a power series expansion is equivalent to the derivative expression here. So in order to have the power series, or in order for a function to be analytic, all the derivatives must exist infinitely many times. But is it vice versa? I mean, if all the derivatives exist, infinitely differentiable, then does it mean the function is analytic? The answer is no. And here's a counterexample. It turns out this function is differentiable infinitely many times. However, it is not analytic. It'll have the radius of convergence 0. So how does that work? First, let's find the derivatives whenever t is not equal to 0. That is, simply take the derivative from this one, disregard this part. First derivative, using the power rule, we get that, all right. And second derivative, we have to use the product rule and power rule, and it turns out some polynomial expression of t to the negative first power times exponential. And here's the third derivative. And again, we take the like terms together in the end. You see, we have to take the derivative from here, like this, and the derivative, no, this stays the same, derivative of exponential, and put those together because exponentials are common. Then we have polynomial expression of t to the some negative power. So we're going to get this kind of expression. Now let's take the derivative at t equal to 0. Just put it into the definition. When h is going to 0, f of h minus f of 0 over h minus 0. Take the limit. F of h is this exponential of negative 1 over h squared. And then what do we have? We have 1 over h over exponential because it's to the negative power, so you can always push it downstairs. And then this limit computation is a bit difficult to handle, so we take the change of variable. Take x as 1 over h, then instead of h going to 0, we get x going to infinity. Take x is 1 over h, then h goes to 0 means x going to infinity, and then we get that. By the way, if x goes to negative infinity, again the same thing because negative 0 is 0. So yeah, okay, maybe it's better to have plus or minus infinity there. It doesn't change anything. How about the second derivative? Because the first derivative is 0, f prime of 0 here is 0. You see, this is derivative, definition of the derivative, but we have derivative function already. So that's the second derivative, but f prime of 0 is 0. We already proved it here. So we have this expression, so the derivative over h, and then if you simplify again, we're going to get e to the 1 over h squared, and then we have some reciprocal expression. So again, we're going to get limit as x going to infinity instead of h going to 0, and we have polynomial expression of x over e to the x squared. Again, let's put plus or minus infinity there. That's going to be 0. How about the third derivative? The same deal, actually. The definition of the derivative, but the second derivative, f double prime of 0 is 0, as you calculated over there. So that's 0, so you can express like this, and some polynomial expression of 1 over h there. And then bring this one downstairs. Okay, and then this h goes up by 1 over h, so you have another polynomial expression. Polynomial expression of 1 over h, or h to the negative first power, if you will. And then you change it into x. What do you get? We have polynomial expression of x. And then we have exponential. So you can take L'Hopital's rule whatever many times. You're going to go down to 0 again. And the same thing repeats. We're going to have polynomial expression of 1 over h over exponential of 1 over h squared. So polynomial expression of x over e to the x squared. And they all go down to 0 for arbitrary derivative. For detail, you can use mathematical induction if you want to, but I don't think that's really necessary because it's quite clear you're getting polynomial expression of 1 over t like that. So in the end, the Taylor series expansion turns out to be all 0, but this is not a 0 function. It's 0 only for t equal to 0 only. So the radius of convergence is 0. valid only for t equal to 0, otherwise invalid. So this function is not analytic. Differentiable infinitely many times, yes, but not analytic. Let's go back to the definition of the analytic function here. You see, Taylor series expansion is valid. That's the condition for analytic function. But in order to have this Taylor series expansion, all the derivative must exist. So analytic is actually stronger than differentiable infinitely many times. Are they the same? No, not the same level. As you saw in the previous example, differentiable infinitely many times is not as strong as the analytic because we saw counterexample. There is an example of a function which is differentiable infinitely many times, but it's not analytic. It does not have valid power series expansion. So they are a little bit different. And as for the quantum leap of solving a differential equation when all those coefficient function and everything is differentiable infinitely many times versus analytic, that's a huge jump. Theoretically, that's a huge jump. And solving a differential equation under the condition of differentiable only infinitely many times is a lot harder than solving a differential equation where we assume analyticity, to tell the truth. Okay, let's stop here.